Good morning, everyone. Welcome to CptS 317 on this Wednesday, April 29th. We are just one final day of lectures away from finals week next week. And so I'm going to go get started with today. And as I mentioned on Monday, the goal for this week is not to get new things, but rather finish up and get ready for finals. And so I called today's discussion review and wrap up. And so to be quite exact, I would probably say more of a wrap up, and then we'll look back at the topics we have covered towards the end. And what we will do on Friday will be review or introduce the final exam. And so that's what we'll be doing today. And there was a question on the group chat about midterm 2, which we have had a discussion on, and the results are out. So let me get started. I know people have come, and if there is somebody who would come a minute or so late, they would be okay. And so let me get to where I need to be and start. So when we met on Monday, we had an agenda that had three items on it, the agenda for the week. And so what we did on Monday was finish up the time complexity or complexity theory portion of the course we had, and then I used a good portion of the time to talk about or give you feedback on homework 6. If you are on top of things, so you would know that there are 8 homeworks we are dealing with in this course this semester. And because of midterm 2, exactly the question we were asked now on the group chat, because of midterm 2, and we wanted to grade that and give feedback, homework 6, which happened before midterm 2 happened, was delayed. And so it was graded and finished. And so there were certain things that I wanted you to have look back at them. And so we used last lecture's portion of time to review or get feedback on homework 6. I would like to do something similar today, but this is going to be for homework 7. Homework 7 is not graded, it is not finished, and we are, James is just about getting started in a little bit, and so we've got some ideas for a few of them, but they're not completely graded. By Friday, when I come, the goal will be to have homework 7 completely graded, and so you will have your feedbacks on OSBL. But what I thought would be a good thing to do, because the final will be introduced on Friday, will be to get solutions for homework 7 and get feedback. So you don't have the grades yet, but I would use the time to work through the solutions for homework 7, and this will be maybe more than half the time for today's discussion, because this one was among the latest topics we have covered, and it was the one that you submitted on Friday, April 24th, this is when you had turned it in. And so seeing how things are on that one and getting a feedback will be useful, getting a solution on it would be useful. When this lecture is over and I post the slides and the video recordings, just like that, the solutions for homework 7 will separately be posted, just like we've done for homework 1, homework 2, homework 3, homework 5, and 6. So it will be posted right after this discussion. So a good portion of the class will be used to go through homework 7, get feedback on it, see the solutions for them, and then we will use the rest of the time to review back what topics we've covered and how things were distributed. Friday, May 1st, will be the day when the final exam, which is a take-home exam, will be introduced. And you have seen how that works, because when your midterm 2 happened, it was on a Friday also. And so we did do that time. So that will be the time when I would say what the exam is, what the questions are, answer some clarification questions, and then so you make sure that you will be there on Friday. I'll come back to that one. So the agenda for today is to walk through homework 7, and then review the course and topics we covered. Anytime you have a question, of course, you should unmute yourself and ask. We are going to be using the group chat as needed for discussion. And so if you have questions, you follow along there too. And so if there are some slides where you would want to take notes, you would take notes, but this is a review basically. So we're not going to be learning necessarily new things. All right, one way in which we can, I think an effective way, we can look back and review things, and in preparation for your exams would be to look back at the homeworks we have done. The homeworks we have done have thematically followed along what topics we covered, and each one of them had a set of problems that would make you apply what you learned, solve problems and things like that. So I did do an overview of these homeworks we've done so far last time in last lecture, and I want to do something similar today, but I want to spell out what has happened before spring break, because my focus last time was on things that have happened after spring break. Remember, the time will be devoted to discussing homework 7, the solution for it, but this is an overview. So the 5 homeworks we did before spring break are homework 1 to 5 were out and in January, in February timeframe. And so I have also put the dates that these things have happened. And one of the things that you would do when you are done with this lecture and when before you get to Friday, hopefully, will be to get a chance, especially on places where you need to go back and look at things. But all of the homeworks will be a good preparation for them, will be for you to look at the solutions your own and the ones that are posted to see them. And so I have tried to see what the topics covered in each one of these homeworks were, what they were out, when they were in, but what topics they covered. And they go progressively. And we've had that tradition of having a week where we would look back at things that have happened in the previous week, and one of the questions would be on a week that was current. So they were looking back and forth in a way. That was how the teams were constructed. And so homework 1 dealt with some very basic things that we began in the semester with mathematical notions and proofs and proof ideas. And then there was a question or 2 on finite automata. Homework 2 were about NFAs and DFAs, regular expressions. And that happened when January was about to end. Homework 3 dealt with more of regular expressions and deterministic finite automata and how they could be converted to generalized NFA conversions. And we worked on things that have to do with NFA to DFA conversion and language that are not regular. So pumping lemma is one technique we have learned to use when things are non-regular language. And so homework 3 and homework 4, also had a little bit of pumping lemma, and homework 4, in addition to regular expressions, had NFA to DFA conversion. And so those were basically around the first chapter, in a way, in the book about regular expressions, where what homework 2, homework 3, and homework 4 were focusing on. Homework 5 is the first homework where we went on to context-free grammars, and I'll come back to these topics when we start reviewing the course towards the end. But then there was ambiguity, there was push-down automata that came in, so context-free grammars, then conversion to push-down automata, and then the conversion of context-free grammars to Chomsky normal form. And pumping lemma made another appearance there, where we were looking at language that are non-context-free languages. So we've got the traditional pumping lemma for non-regular languages, and then a pumping lemma for non-context-free languages. And so homework 5 dealt with one problem that has to do with that. And we ended with midterm, and that happened end of February. And this is how things were pre-spring break. So I enumerated at least 1 to 5 last time, but I didn't spell out the dates that they were out and in, and what topics were covered. What happened after that in terms of homeworks and in the exams after spring break was we had 3 homeworks. 6 is what we discussed, in fact, last time in terms of solution, but the topic was context-free language, an extension of what we had done before spring break, but just to get familiar with the concepts again, but that was not a topic. The topic that we started in after spring break is Turing machines, but this one had a look back at a couple of them, especially some things that were in homework 5 and you needed a little bit of mastery on. Otherwise, a good portion of homework 6 was about Turing machines. Homework 7 was exclusively about Turing machines and decidability. And we did spend about 4 lectures or so on Turing machines and 3 or 4 lectures about the decidability. And I'll come back and look at them when we finish this one. But that was what homework 7 dealt with. Homework 8 is the one that you have submitted or you're yet to submit on Friday. And I'll tell you what I think will be a good idea for you to do in terms of that one, time-wise, that is. Waiting until Friday is great, but if you can't, just so you get more time for your preparations, it will be good if you submit. I know there are some of you who have, but I understand if you still want to use the rest of the time until Friday. That is a homework that focused on the latest topics we've covered: decidability, reducibility, and a portion about the last 3 lectures that has got on time complexity. And so that's homework 8. We are not going to have a chance to go over it for solutions, but you will get a solution for it by the time you would have your finals in a way. But homework 1 up to homework 7, you will have everything you need in terms of preparation. And the reason I'm choosing to go over the solutions for homework 7 now is a way of preparation. Other than these homeworks, we have also dealt with midterm 2 after spring break, and the final is to come on Friday. And so I wanted this one slide for you to just look at how the homeworks were distributed and what topics were covered. And this will be an excellent way for you to review when you get ready for your finals. So everything except homework 7. Homework 1 to homework 6 are graded. The grades are on Oswald, and you have solutions for them. Homework 7 is not graded, but you will have the solution today posted, and I will spend some time discussing it. And we have taken time to both get feedback and walk through things that we have done in midterm exam in one of the lectures. In fact, I think it was 3 or 4 lectures. So this is my goal for today, to start with having a review of homework 7, and then we will start reviewing the course. Okay, I hope everybody is on board and following me along. If you have questions, then again, I want to remind you to ask me as we go forward. Okay, so what did we have to do in homework 7? Like every other homework, we had 6 problems. I'm going to have the problems laid out like this first, and then we will we'll go through each problem one at a time. So we had something that has got to do with closure properties for decidable language. That was problem 1. Problem 2 had to do with something that came up when we discussed decidability, and then there was this idea, or Hilbert's problem, his 10th problem about polynomials, whether they're integral, the roots are integral, and we said that the single variable version of that question is decidable, and the problem that you were asked to show had to show a bound on it, and that was problem 2. Problem 3 was showing a particular language called AllDFA, and see, we've seen this in this decidable language type of discussion. Most of them made us go back a good portion of the course that we've covered. There were things that were formulated around finite automata. There were things that were formulated around context-free grammars. There were things that were formulated around Turing machines in general. And so that was a very nice collection of things, and also a nice way to tie things together. And so this particular language asked you to show that this language, which is the negative of an the complement of an empty DFA, that is decidable, was problem 3. Problem 4 had to do something around uncountable. As said, we have learned when we started talking about decidable language and so on, that not all infinite sets are created equal. So some infinite sets are countable and others are uncountable. And we call them countable when we can map them to natural numbers. If there is a one-to-one mapping, we can do that. Oh, we can count them. If not, then we say we are not able to count them, and we saw the diagonalization technique and counter and things like that. So this problem picked up on one sequence, and you were asked to show that it is uncountable. Problem 5 has some weird starting point in a way that you needed to define certain things, and then you were to show that if you have 2 languages that are co-Turing recognizable, they can be separated by some decidable language. And so there's some technical things you need before you get there. So I'm going to go through the problem, so don't worry about if you don't remember them. But the ones that we have seen, even though we haven't graded a whole lot of them, the way things are starting to look out good. And so I'm sure all of you have worked hard in trying to solve these problems. And so you can be assured by the time you see the solutions now, you either have got them exactly right or you're very close. But I can't say about every assignment, but because we haven't finished grading. And the last one was Magic the Gathering. a game that turned out to be the third most popular game in the class, according to what you told me some lectures ago. And so there were some other games that were more popular than Magic the Gathering, but it had the third place, and there was some pretty hard question on it that talked about whether you can say that this thing can know when things are on a tie. And so I will tell you what the answer for that question is. All right, let's go now through these problems. So now this is a time when you bring yourselves together and try to pay attention to a little bit of detail. So first, let me acknowledge one thing. Whenever you see here what I'm doing now, you should not worry, because the solutions for this one typed up, just like we have done for the first 6 homeworks, are going to be posted. And so what you see here is my pulling out of the solution we've prepared and putting them in this slide for the purpose of a good discussion now. So don't try to take notes, and I'm not going to, this is not an eye test. So if you are not able to see everything in big fonts right there, when you see these solutions, don't worry, you will have that posted. But I think this is large enough, even for me, who needs to change his glass every year. When I go to my eye doctor, I can see this on my screen. So it should be large enough. But let's walk through each one of these problems. So problem 1 had to do with showing decidable language. Okay, in your exam, you will be asked questions like this, some of them, right? We'll see them on Friday. But whenever you are asked and there is something that says show that this language is decidable, that means come up with a Turing machine that does the job. That's what it means. And when it is undecidable, you know what it means. It means that you are going to be doing some reduction and then argue that this thing was undecidable. I reduced it to this one, and therefore it is not. It is undecidable. That's how you would go. So showing that it is decidable means come up with a Turing machine. The problems in this one, there were 3, and you have, I think most of you have done a good job, could be said in other books and something like that. And they may be formulated as results, and you can say, here's a theorem. I have, this collection of decidable language is closed under concatenation. Boom, there is a theorem. We could do that. So now it is formed in forms of a problem, and we are going to show it. So you're adding to the lectures, basically, or whatever it is, the knowledge you have around decidable language is one way to see it. So they had 3 parts, and so we're going to start with 1A. And so it said the collection of decidable show that this is closed under concatenation. We may remember, we have seen other languages in the class before where things are closed under concatenation. What does closed under something means? It means if I have 2 languages that belong to the certain language, after the operation is carried out, the resulting language is also included in that class. That's what closure means. And so if we have 2 decidable languages, L1 and L2, and we concatenate them, then the resulting language is also decidable. Go show that, is the question. So, and the solution here will be formal as much as possible. And so it's cleanly written and things like that. So your own solution might be phrased a little differently and so on. So if you got the crux of the matter, then that's what we'll be looking for when we create them. So if you have 2 decidable languages, L and 1, let's call the Turing machines that decide them, because they are decidable, M1 and M2. And we are going to construct now a new Turing machine called M prime that would decide the concatenation of N1 and N2. And how is it going to work? We are going to take an input string W, and now we are going to cut W into pieces, into 2 parts, W1 and W2. And so we will say it's a concatenation when one part follows the other one. That's what the definition of a concatenation is. So for each way to cut it, because there are multiple ways to cut in a string, and you might remember now, if you go back to how things were in regular language and context-free language, when we talked about them, we had to argue in a similar fashion whether this was closed or not. And so for every possible way, for each way we can cut a string into 2 parts, W1 and W2, we are going to run our first machine, which is going to be run on W1, and we are going to run our second machine, which is going to run on W2. And if both of them accept, now the concatenation is welcome in the new one, so we accept. If not, we continue to cut to the next cut, and we do and do and do. If all cuts have been tried and none of them work, then there is no concatenation. concatenation, because that's what concatenation means. So we don't know what to cut, right? So we have to try everything. And so by the time we have tried every possible way to cut this thing and none of them accepted, then there is no way that this one will be, otherwise we'll cut. So here is a Turing machine that would decide the concatenation of two strings, and therefore it is decidable. Our Turing machine is capable of doing that job, and we presented it. That's what we are asked to do. We were asked in part B to do an exact same argument or the same question, but this time we're going to do with the star operation, and you know what the star operation is. This is very much familiar. So if you have a string, so however many lengths it has, starting from the empty strings, so all of them, right? So we have basically the same thing, and we're going to have a decidable language, and we will call M that decides it. And we're going to construct now a new Turing machine, M prime, that decides the star of L. And what do? We take on input, and now in the concatenation case, we just needed to cut it into two, and then show if there is a way to split it into two, where the first one is accepted by the first machine and the second one is accepted by the second machine. Both of them accepted them, and so we'll say the concatenation is accepted. Now we've got many, and so we have to cut it into parts like W1, W2, Wn, and we're going to try now on each one of these pieces. We run M, and then if M accepts any of these strings, that means at least there is one place where the star operation's length has been decided, then we accept. If all cuts have been tried and there is no place where we have succeeded, then we reject, and therefore the star operation is decided also. That means if the original language was decidable, the star operation on it, anything that we would get by applying the star operation will also be decidable. In other words, the collection of a decidable language is closed under the star operation. How about complementation? That was part 3, and this one is easier. Complementation means negation. So if you've got a language, the complement of that language is everything in the universe except whatever was in that language. That's what a complement is. So what do we need to do? If we had a decidable language L, and M was the Turing machine that decides it, then we do the opposite of what M does for our new Turing machine, M prime, to be able to do the complement. That's basically what it is, and the result, therefore, is a lot more concise. So for any decidable language L, if M is a Turing machine that decides L, then we can construct another Turing machine, M prime, that decides the complement of L by just swapping the accept and the rejecting states of M. If you've done it this way, then it means you will be guaranteed to get a full credit on this one. And if you are close enough and you have phrased it slightly different, some of you actually would phrase this one a lot better than what I have done here. And I have been impressed enough times in other homeworks and other things to say that our solutions are not the best, but they are good representative and they are correct. And some of them may be better than some of you. Okay, I will admit that. But I think there are some of you who would say them a lot more elegant than what we've done here. All right, problem 2 was about bounds. And
I have a quick question about 1B.
Okay.
Before we get too far forward.
Sure, that's an excellent place to ask.
I said that if I used that we knew that that they're closed under concatenation, and so that the star operation is just concatenation with itself any number of times. So I said that, like, if you can concatenate it once, you can concatenate it a second time and a third, all the way up to n. Does that?
That would also be a good argument, and you are right in saying that. So this is a generalization, and so the reason this is a good place to make a comment on something when you are asked about proofs. And we'll come back to the end of the class now. When we review, we said, oh, we learned a thing or two about how to prove things. So this is a proof of a kind, right? So when you have to show something and you show first the general case, then you could say this case is only a special case of it, and you are not burdened with too many things. You show how to drive from Pullman to anywhere in the world, and then I shouldn't say anywhere in Washington. And if you should give me an algorithm for it, then if I ask you how do you drive to Seattle, you will say, oh, that's only a special case, and you will be forgiven. There is nothing that you have to do. So in this case, if you had started with the general case, then you would do. But what you have argued for now is not starting from the general case and then show this is just a special case. You're saying you have to repeatedly apply, and you just correctly said that. So the argument is correct, but you should make sure that those distinctions are made. Some cases you would say, I have this one, and then I'm going to repeatedly apply it as many times as I need to get to this general case. Fine, which is what you have argued. In other cases, you would say, here is one general case, and then this other one will follow along because it's a special case. But that solution was correct. All right.
Cool.
So,
thank you.
Sure. Anybody else has got any question on problem 1? All right, problem 1 was good. Problem 2 was math. And I wrote this one out explicitly. When we talked about this thing, and when I gave you a hint, I have already given you the hint that I need. So it will be a waste of time now if I repeat the same amount of time I spent last time. But here is when it is completely written. Here again, I would expect somebody to be even more careful. There is 1 or 2 places where I actually wanted to have a simpler argument, so I haven't gotten to too many details, but this is how you would write. Sometimes you've seen enough examples. You've seen enough examples when you know something to be shown intuitively made sense, and so you say, why are they asking me to show this more formally? It's so obvious. Sometimes you do actually have to have that rigor to formally argue, go from one step to the next step, and every single one of them has got a natural, logical step to it, and it is tight. That means you are actually not waving your hands, but exactly showing what it should be. That is a practice you should have. And so this is more of an exercise of that type. And you've seen in math, whatever that one is called, 216, or other things like that, where you need to have formal proofs. And so there is a bound here. The more important thing I want you to remember is that the single variable case is whether its root is integral is a decidable problem in a stark contrast to every other case, because now we have a bound where we can show. The people who showed that this general Hilbert's tens problem, where we have a polynomial and determining whether its roots are integral is undecidable, kind of is harder because you're showing an impossibility result, but their argument is to say that there is no bound that one can give. So by doing that, you can say there is no way for me now to be able to have a search space in which I can explore, because that is unbounded, and so I have to, it's undecidable. Whereas in this case it is. And so here is how the procedure would work through. So we have talked through this, and you see it now. So let me just move on because we have spent enough time. All right, problem 3 said AllDFA is decidable. What is AllDFA? AllDFA is DFA that recognizes everything. So the alphabet with the star operation on it. So everything is accepted is what AllDFA means. And so it's the subscript DFA shows that there exists this deterministic finite automata that recognizes this language. And so you're asked to show that this is decidable. And I think I remember somebody asked it during the lecture when we introduced the problem, how to go about it, and they said the right thing at that time. And here is the Turing machine that does the job. We will call this Turing machine L, the one that recognizes AllDFA. So it will take the description, and here are the kind of details you should remember, whether it is in exams or any other thing. You should pay attention to what the input is. So you should generally say, we say here is the input, and it's an encoding of the string. This time it is an encoding of the DFA itself. And so on that input, we are going to construct a DFA B that recognizes the complement of AllDFA, and the complement of AllDFA is empty. So we've got everything, a complement of it is empty. And there is a theorem we have seen in the class, and we discussed that deciding that one using a Turing machine is decidable. And so EDFA, that is what we call it. So we run that machine, we get the answer, and we repeat that answer. And now there we have it. So AllDFA is decidable, and with nice clean 3 statements like this. If you have not formally said this, but you just say that this relationship between AllDFA and EDFA is established because one is the complement of the other, and we know that EDFA is decidable, and therefore AllDFA is also decidable. If you have said it that way, which I know some of you have, you are perfectly fine. This will be a more formal way of saying it. All right, problem 4 was about an infinite sequence over the binary alphabet 0, 1, and you were to show that this is uncountable. counterdid this stuff. And we call that one diagonalization. And our goal now is, first of all, the way this one works, and if you remember how things around the pumping lemma also works, is to show by contradiction. And therefore now, to use diagonalization, that was the prompt itself, said, show that this particular infinite sequence is uncountable using diagonalization, was already in the prompt. And so to do that, it means you have to exhibit a case where you can construct such that the thing that would have made it countable, which would be a mapping from the set of natural numbers to this set that we are busy with, if there was such a mapping, then it would have been countable. And so we would assume that there is such a thing, and then we would construct something that would be a contradiction because of its existence that doesn't satisfy this, and therefore we arrive at a contradiction. So without even having to nail down exactly how we are going to get that special case, we know the strategy. That is what we would have done. I would like to believe that many of you have gotten it. I have no way of knowing it, but here is how you would solve it. Suppose, and now this fancy B is a B. In the title, I wrote a B because I don't know how to write a fancy B in PowerPoint, but in LaTeX we can. So this fancy B is countable. We are going to assume for the purpose of arriving at a contradiction. And we are going to say this correspondence now that takes us from the set of natural numbers to B exists, and we'll call it F. And now we're going to construct an X in B that is not paired with anything in the natural numbers. That's why it's not countable. And so we're going to prove that, and then we will say, let X, the one that we will construct, be called X1, X2, and it will go forever because this is an infinite sequence. And we're going to construct it in this fashion. And this is where the ingenuity would come, or where the cleverness would come. There might be some other way of doing it. This is the way I know. And this will be maybe more like in practice of something similar for other problems, a similar spirit. So let xi, we'll call xi equal to 0 if I'll tell you what f of I means. F of I, when the i's part of it is 1, when it is 1, we'll call xi 0, and when, we'll call xi 1 when f of I is 0. So we'll do the opposite in a way. And what is f of I of I? That's the i's bit of f of I. So we are now, remember the diagonalization idea? So this I stuff should tell you that we are actually on the diagonal. So you've got f of I, and you can think of it as its values going through the rows all the way to infinity, and then we've got another I, and then we've got a thing that would go to infinity, and so on. So if we have that table in our head, and we are looking at what happens on the diagonal, that's what we are referring to with this f of I, that stuff. And so xi will call it 0 if f of I on that diagonal is a 1, and we'll call it a 1 if it is a 0. Now, by doing this, we ensure that x is different from f of I for any I, because it differs from f of I in the i's symbol, and therefore it becomes a contradiction. That means now we cannot have that mapping, it cannot exist, and therefore, because we can always construct something like this, then it means then we have exhibited one case where we cannot form, and therefore we have shown this to be an infinite sequence by diagonalization. If you've gotten this one, I will be very impressed, and it will be nice, and you will get full credit. If not, then now you get one more example of how to do diagonalization. If there was ever to come a question on how to use diagonalization, then you would be able to use it. But it is a nice, cute example. In fact, nicer than the one that we saw to introduce what diagonalization is in the lecture proper. We are on problem 4. We've got 2 to go. Let me see if there is anybody who's got any questions so far. Okay, I am assuming you are all with me. Problem 5. Problem 5 could be a problem where it was harder. You had to struggle a bit, but let's break it down. So let me actually get the prompt of the question itself out for me to see. So it had to do with co-Turing recognizable languages. We had Turing recognizable languages. That is the set of languages that is Turing recognizable. And then within Turing recognizable, we've got some decidable ones. And there are some that are not decidable, but still are Turing recognizable. And so if we take Turing recognizable language and see the complement of it, then And if that is recognizable, we will call it co-Turing recognizable. So a co-Turing recognizable language is a language that is the complement of a language that is Turing recognizable. We will call that one co-Turing recognizable. So we're going to take two co-Turing recognizable languages, and we will call them, and then they will be disjoint, okay? And we will call a language C separate as A and B. This is the word where the word separable is defined in the prompt. That's why I'm reading it. So we'll call a language C separates A and B. If A and B to begin with were disjoint, if A is contained in C, C is the one that is separating them, and B complement is contained in C complement. So I've got this language C, it would contain A, strictly contain it, so A is a subset of B, and it would, the complement of it would strictly contain B, then it means it is separating them. Why is it separating them? Because C contained A, and C complement contained B, and therefore it is able to separate them. We'll call that language we will call that language C, the one that separates A and B. So what we are asked to show now is any two disjoint co-Turing recognizable language are separable by some decidable language. So there is one Turing decidable language that would separate two that are disjoint co-Turing recognizable language. So there is a bit of parsing to do before you get to solve the problem itself. Okay, now that I have recapped what the problem was, let's see how to go about solving it. So we'll call A and B the two languages such that their intersection is empty set. And we know because they are co-Turing recognizable, A complement and B complement are recognizable. That's exactly what the co-Turing recognizable language definition means. So we'll call the language that recognizes A complement J. So J will be the Turing machine that recognizes A complement, and K be the Turing machine that recognizes B complement. What we will show now is that the language decided by the Turing machine T, a new one that we will construct, will separate A and B. They were disjoint, they were co-Turing recognizable. Now we're going to construct a Turing machine T that separates them. So what is it going to do? It's going to take on input W, and it's going to simulate J, the one that recognized A complement, on K. And we are going to simulate J and K on W by doing this thing in an alternating state. So the two machines are going to work alternatively. So J is the one that recognizes A prime, K is that recognizes B prime, and we are going to make to simulate these two machines on W by alternating one at a time. Now what we will do is if J accepts the first one, that means J accepts A complement, then we reject. If K accepts, that was J, the one that recognizes A complement. If K accepts the first one, then we accept. If we do this successfully, then we have been able to separate them because the definition for separation is for the separator to contain A and for the complement of B to be contained in the complement of C. That's how it has separated them. So the second part now is telling you how it is doing the containing one and the containing the complement of the other one. So the text below those two lines, the Turing machine is finished. By the time the first and the second steps are defined, it is finished. So the algorithm would it terminate? It would terminate because we have the complement of A union the complement of B. That means everything is all the alphabets, sigma star. So either J or K will accept W eventually when we do this thing step by step, alternatively one after another, after another, after another. One of them will accept W eventually, and therefore it will terminate. And A is contained in C because if our input string W was in A, then W will not be recognized by J because J is a recognizer for A complement, and W will be accepted by K first, right? If B is contained in C complement, so that was the first portion for making C a separator. A is contained in C. The second portion is B is contained in C complement, and we are going to argue for that. B is contained in C complement because if W was in B, then W will not be recognized by K, and will be accepted by J first. And therefore, C separates A and B. Okay, I've written this down. If you have followed me along, perfect. If not, then you will probably need to read this thing one more time. Every single word is carefully chosen there and precise, and probably we haven't used even a word more than we need to. We probably could have said more things to elaborate and give examples and things like that, but I think this is a complete proof that I would like to move forward with. All right, problem 6 was about Magic the Gathering, and this was a game that you are more, most of you familiar with. I'm not sure if you read the article that the prompt made reference to, but it was shown to be Turing complete. So there is a formal argument around it. But there was a couple things that were pointed out to you, and you were going to finally, after having seen that, why it's interesting to say. The question was, what problems could arise as a result of these two properties of the game? So there were two properties mentioned. If one were to simulate this game with a computer program, can it always tell if a game is winnable for the players? And explain your answers was what the question was saying. So here's the correct answer for this Magic the Gathering game, and the question around whether it's going to be able to decide whether a game is going to be winnable or not. If a Turing machine is encoded from a game state, we know that no moves can be made until the Turing machine enters an accepting or rejecting state. You would agree with that statement. However, as we will know, it's not guaranteed that any Turing machine will enter either of these states, and it may instead enter an infinite loop. I think this one also you would follow along. If this occurs, the game should tie because of our second property of the game, said in the prompt, but verifying this will be difficult. Why is it difficult? Because we know the hold problem. ATM, you may remember, decide if it accepts this Turing machine, that problem is undecidable. And hold TM, which is the halting problem, that is what is the most famous problem known to be undecidable. And therefore, we cannot tell that because there is no Turing machine that can tell if any other Turing machine will hold on some input. The halting problem is undecidable. That is essentially the crux of this. If you have followed along and seen that, then I think you will correctly answer this question in this way. So if we try to construct a computer simulation of this game, it may turn out that the simulation gets stuck trying to determine if the game should tie. All right, I hope you've had fun and arguing this and getting this point and seeing the connection to the halting problem. And hopefully you have answered it exactly this way or somewhere close. All right, those were the 6 problems about homework 7. I hope this was helpful, and I will make the solution available on Oswald. We've got a little over less than 10 minutes, but we are done. The more important thing that I want to do is done already. So what I will do now is kind of recap on the topics we have covered, and then say a couple of final words, and we'll be done for the day. Okay, so we've covered 3 parts is how the course is organized in a way, and the book is, and the last part was the one that we just did, the last 3 lectures, and was a smallish component. But I wanted also not to forget what we did before part 1 started, and that was an intro where we had some mathematical notions, and that was what homework 1 actually did, and we did say definitions of theorems and proof techniques and things like that. So I don't want it to be outside of the picture when you review and when you think about this one, because it was fundamental, and the book calls it chapter 0. Then we had, this is now part 1, the topics that were covered under part 1 had, the first big topic is regular language, finite automata, deterministic and non-deterministic, regular expressions, and when languages are not regular, chapter 1. Context-free language was the other big topic. Both of these topics were covered before spring break. What did we learn? Context-free grammars, push-down automata. We learned when we were learning regular expressions, things that are expressed using finite automata are exact same class, and they're called regular language, things expressed with regular expressions. And these things look very different from when you look at them from outside, but they are the same class of language. And we've got something equivalent when it comes to context-free language, things that are expressed with grammars and things that are expressed with push-down automata. That was the point, the more important point here. And then we saw when things are non-context-free, and then there was a little bit of a detail that we went into when deterministic context-free language. So there was a bit of things that we will not necessarily need to spend a whole lot of time now when you prepare for your exams. The last point about deterministic context-free language, but that was a topic we covered. That was part 1 of the course. This is also called before spring break. After spring break, we talked about computability. That is where Turing machines would come. We've got 4 or 5 lectures, I think 4, around the Church Turing thesis. We saw Turing machine, the different variations, and the things that is important about Turing machines is their tie to the definition of algorithm. And that's why they helped us come up with things to know when things are decidable, when things are undecidable. That's when the result of Hilbert's tens problem was solved and things like that. That's what the chapter 4 of the book was. And we did spend 3 or 4 lectures on this one. And we separated things into language that are formulated in terms of, in terms of language, how we put them. And then we said there were some things that were decidable. And we learned one that was undecidable using the diagonalization technique. And then thanks to something called reduction to reducibility, we added and added and added a number of other undecidable problems. That was chapter 5, and this was what the problem 6 or homework 6 and 7 touched a little bit on. And we finished that discussion with a special kind of reducibility called mapping reducibility, where there was a MANT1 function that would say how to reduce, and we became a little bit more careful on how reductions are done. That helped us get into an intro into complexity theory, which is what we covered the last 3 lectures. And so time complexity, we saw how things are measured in big O notation and small O notation. We saw now the Turing machines were the ones that carried us through all the way, and they made it into complexity theory also. And so the Turing machines show up there. Here is a Turing machine that does it. Go find the time complexity of it by counting how much it takes. And so we looked at 2 classes of problems, and we said what the class P is, what the class NP is. And the very, very last lecture we had showed us made progress to answering this open question, whether these 2 classes are equal or not. And we looked at problems that are called NP complete that would determine whether finding a solution, polynomial time algorithm for them, would mean everything in NP would also be solved in polynomial time. And the last lecture we had last time that I didn't find time to tell you had 4 problems at the end of slide 18 that are examples of NP complete problems. But you were introduced to those problems before, and so you know them. I think 1 or 2 of them are new, but the other ones came an appearance when we started talking about time complexity in the previous 2 or 3 lectures in that week. And so these were the 3 major parts. Part 3, complexity theory, is a smaller portion. Part 1 and part 2 is what the course is about. And so those were the topics we covered, and we talked about the homeworks. And so I think this is maybe a reminder that we have the 8 homeworks all done, except for homework 8 that is due on Friday now. And we have done our 2 midterms. The policy around homeworks is that they would account, first of all, 60%, and the 2 midterms would account 20%. So you've done 80% of it, depending on when you will submit your homework. 80% of your work in terms of contributions to your final grade is done. The only thing left is 20%. That would be what the final would carry. And in terms of the homeworks, you would have the best 7 out of the 8 count. Make every effort. If you have not done before, if you have done so far the 7, then make sure that you do the 8th one also. And if you have missed one, then you will not have any other choice other than the 7 that you have to be counted. If by any chance you have less than 7, that means there will be a homework where you will have a 0 contribution to the 60% is what it would mean. The 2 midterms would contribute 20, and they would weigh equally. Midterm 1, 10%, midterm 2, 10%, and the final would contribute 20% to your grade. Final words on finals. Prep for the final, review the lectures. We had the things that were before spring break were handwritten. Some of you have your own notes, but I have made the notes available as we go along. And then after that were slides. And the videos are excellent ways to review, not necessarily for all of the lectures, but for the ones that you missed or the ones that you haven't mastered, then reviewing the videos will be an excellent idea. Reviewing the homeworks, both the prompt and the solution will be a good idea. Problem 7 solution will be posted today, and we have talked about it. The other piece of advice I have in terms of preparation for the final is that try to see homework 7, 8 behind you as quickly as possible. So Friday is the deadline, but if you can do it before then, that will be great. And make sure that you will be there on Friday when I will introduce the final exam. And if you need to watch the video afterwards, that will be an excellent way. I think you've done so far a great job. And I know you got this, the finals, and so be ready for what it would look like when you come on Friday. One last word, I'm sure you've gotten email from whatever it is that comes in, but the course evaluation is out, and it has been out, I think, for a few days now. Make sure to complete. You know how to go to MyWSU and do it. And this will be a useful feedback, both for myself, for the college, for the university in general. And so I would encourage you to do that and take care of it. I know you have got more courses to do and things to take care of, but this is important. Your participation there is important. Thanks, and let me see if there is anybody who has. Okay, can you go over the last problem from midterm 2? I will do that on Friday. Obviously today was over. Okay, it's 11. So I hope you have followed me along. I will see you on Friday when I will introduce the final exam, and take care of yourselves, okay? Great, see you then.